Hello and welcome to the Superposition Guys podcast. My name is Yuval, and my guests today are Professor Eduardo Miranda and Brian Siegelwax, authors of Teaching Qubits to Sing, Mission Impossible, a fascinating work about creating music with quantum computers. Eduardo, Brian, and I talk about how the program works, their plans for future work, finishing Schubert's unfinished symphony, and much more. We hope you enjoyed this episode, but before we start, here's an example of those singing qubits.
Ooh, ooh la la, la ooh. La, ooh la la la, ooh la la, ooh la la la, ooh la, ooh la la, la ooh la la, ooh la la, ooh.
Hello, Professor Miranda. Hello, Brian. Thanks for joining me today.
Thank you.
Hello.
So, Eduardo, who are you and what do you do?
I am Eduardo Miranda. I am a professor in computer music at the University of Plymouth. And currently, I am developing research into using quantum computers to create music.
And Brian, who are you and what do you do?
I am Brian Siegelwax. I write code, I write about code, and I also recruit people who write code.
Fantastic. And we are here to talk about singing qubits, right? The qubit choir. Eduardo, you've been on the Qubit Guys podcast before, and I know you're using quantum computers to compose music. Could one of you or both of you tell me how this Singing Qubits project came about?
Well, I think Brian and I have been communicating in social media, exchanging some ideas and so on. And I think naturally I think both of us wanted to develop something together, and then I think the opportunity to develop a generative music system came about. We exchanged some ideas about how we could implement, how we could find a simple way to program a quantum computer to generate sequences of things. And this, Brian can probably tell you a little bit more about how technical idea came up, but the uh, the inspiration I had was well, if you can generate sequences of musical notes, what would be an interesting instrument to play those sequences? And at the time, coincidentally, I was working with vocal synthesis. Then I said, okay, so let's hook this quantum system to a vocal synthesizer and let's make the qubits to sing.
So Brian, if I understand correctly, there's a vocal synthesizer, which means that I could put in any file or collection of notes and it would generate the singing sound. And the quantum part is the part that composes the sequence of the notes. Is that correct?
Correct. So we started with a sample file and we use that to generate the rules, and then the rules get encoded into the amplitudes of the qubits, and then the qubits decide what the sequence will be.
So let me get this straight. So if I have, you know, do, re, mi, fa, sol, la, si, in, usually the next note would be a do, right? Or in English, A,
Mhm.
B, C, D, E, F, G, and then A. So that sounds like a probabilistic state machine, right? You
Correct.
say, well, if
Correct.
this is the sequence, then the next node with high probability or with some probability is this, and that, and so on.
That's it.
How is that different than the quantum generation?
Okay, so the system has two phases, what we call a learning phase and a generative phase. The learning phase is pretty classical, so to speak. What we do, we input music into the system, then we statistically measure, how many times not X follows not Y, or how many times three notes follow other four notes, things like that. So we build a set of rules. Then we put these rules into what would be the equivalent of a transition matrix. Okay, and then so that is the learning phase. So we can input anything, any musical sequences to the system will work out what these rules are. Then the classical way of doing this would be to program the machine to go through this transition table and pick notes that would follow certain probabilistic, Gaussian or whatever tendencies. But we found an easier way to do that, which is use the quantum machine to build quantum states with the amplitudes reflecting those probabilities. So it is a much more, in my view, elegant way, and I think we can scale this up in the future uh, much easier than if we were going to continue doing this classically.
So, Brian, maybe you could talk to me a little bit about what's going on the inside. How does the quantum circuit look? How do you prepare the state? What are you measuring on the output? Could you tell me a little bit about that, please?
Yeah, the interesting thing is there's no one circuit to show. They're all generated on the fly. So let's say we want to use three notes to generate the next note, and let's say we have A, B, C, and we go through this original tune, and we're counting how many times ABC appears. So let's say, for argument's sake, ABC appears 10 times, and 7 times the next note in the sequence is D, and 3 times the next note in the sequence is E. And they're all binary coded. So let's say 000 is A, 001 is B, and so forth. So what we have is, and from your standpoint, Yuval, it's the classic state preparation function. So we want 0% probability of 000A, 0 for B, 0 for C, then 70% for D, 30% for E, 0 for the others. So you have 8 probabilities, except that we used Qiskit's initialize function, which requires us to convert that into amplitude. So we have to take the square root of the probabilities. We have to take one extra step. And then the initialize function generates the circuit on the fly. So it'll generate a circuit in this case that when we measure it, we'll have a 70% probability of measuring 1 0. I got ahead of myself. What's D? 1 0? 1 1? Whatever it is. But 0 1 1, I think, which is D, and then 1 0 0 or whatever E is. And then let's say we measure D. I should be able to do this in my head faster. But anyway, so then we have B, C, D as the sequence. Then we look back in the transition matrix, and we have another round of amplitudes. And the initialized function generates a completely different circuit that, when measured, produces the output in the probabilities that, not that we want, but the probabilities that came from that original file. So you end up with a tune that sounds somewhat like the original, but depending on how many notes we use, we can alter how much it sounds like the original, how much it sounds different, how much variety there is. But the core piece, the quantum piece, is is generating those circuits that get measured in the probabilities for the allowed next notes.
And what type of music did you use as input? Was it Bach? Was it the Beatles? Was it Beethoven? What was going on there?
We use a number of things. I mean, we use classical melodies, classical music melodies like Bach, Mozart, whatever, and then we. It so happened that I had a few MIDI files for film music, and So we had this quirk idea. Let's use the for the paper the tune of from the Mission Impossible film, because it's kind of is it possible to program qubits to sing? Is it a mission impossible? No, it is not. It is possible. So that is the tunes that are mentioned in the paper are from the Mission Impossible theme, and we also use a Bach a cello sequence to show that it's generic, what we do.
Was there a particular type of music that worked better, that was more deterministic, or that was easier to sort of follow?
No, I think because we are dealing with probabilities, it's a stochastic model. Those inputs that are more repetitive will tend to generate music that are more similar to the input. But those pieces of music where the notes vary more, where, there are no obvious a beat or a pattern that you can identify quite immediately. So these for me as a composer generate more interesting results. What we are doing now is trying to go beyond the the only generated sequences of notes, um, because I think now we have the beauty of this core quantum algorithm that generates sequences. What I'm going to do now is to provide Brian with codes that would represent other things in the composition. For example, dynamics, speed, maybe more voices. And because we are dealing with speech synthesis, there are things in speech that are quite interesting, like uh, intonation, prosody, things that relate quite well with speech research. So I think that what we are doing can have a nice connection with quantum natural language processing, for example. These works are very symbolic. They are looking just at written words, but I think we have a potential here to add the synthesis part, the actual rendering of the speech, which will then give another dimension to language, which is the inflection of the speech, the emotions, and things like that. So I think this is where music can fit in quite interesting in scientific research.
You mentioned speed and dynamics, but the current circuit generates the melody. Are you
Correct.
working on generating the harmony as well?
Yes, we are doing that. So, um, of course, the encoding of these materials will kind of explode the dimensions what we are dealing with. So at the moment we have two dimensions, which is pitch and the duration of the note. But if we begin to add other elements, like what instruments plays this, what's the loudness of this note, how do we actually play it? Is it a plucked string? Is it a bowed string? Is it a consonant? Is it a vowel? So once you begin to add these other dimensions, then it's here where I think the quantum computation will become quite powerful.
I assume this still needs, or for the foreseeable future, this is still going to need a lot of human supervision. So, for instance, how would the quantum computer know when the piece ends and how to end it? Usually, I mean, you might end it on a dominant note or something else. How would that work, for instance?
Um, I think it's possible to automate this as well. I mean, it's not. I think these are what we say the cherry on the cake, so to speak. After we've got the core thing working, then I believe that the details can be honed, and further incorporated into the formalisms. So these are things that I needed to liaise very close with Brian so that we keep the beauty of the model, but use what we've got and try to scale it up. to more number of qubits and so on.
There was a book that was quite popular several years ago called Sleeping with Schubert, and it was about this lady who became obsessed. Something got into her, and she started thinking like Schubert, and then of course she also finished the unfinished symphony. How far in the future do you think that you'll be able to automatically finish the unfinished?
Um, I think technology for doing this, we more or less know how to do this because there are examples of composers that programmed, classic AI to do this sort of thing. So we've got the Mahler symphony finished. We've got the Schubert symphony finished. We have a Beethoven symphony finished. So there are, of course, these outputs are not, I would say, very realistic in the sense that it's easy to spot that was done by a machine. But the know-how for doing this, I think it is already out there. What we need to do is to perfect this, and I believe that my because I am so enthusiastic about the quantum computing world, I think these new ways of thinking about programming AI will lead to this sort of things that you just mentioned. So maybe the dream may be quite realistic. I think pretty soon.
Brian, from a quantum perspective, what did you learn doing this project? Obviously, I'm guessing you learned a lot about music and about composition, but how did you become a better quantum circuit designer with this project?
I have to go back about 2 years. I was, well, I like this story. I was reading a paper a day off of archive. I was getting most of the suggestions from Twitter. Somehow I discovered a paper from Professor Miranda called Quantum Computer Hello Music. And it blew my mind. And we've worked together, and it still blows my mind. But the key difference with quantum music, and I would compare it to quantum gaming, where you generate some random numbers and you can use it during the game. You can generate some random numbers and you can generate terrain. But the interesting thing about music is it has to sound good. And that's very subjective. And I have no musical talent whatsoever. So when we're playing back these tunes, and sometimes it's, kind of catchy, it sounds kind of interesting, it's the original's in there, but there's that little bit of variety that sounds good. It just blew my mind. And as we were working on it, and still as we chat now, I think about all the other possibilities because we started off very simple because we he Professor Miranda said about getting the core working, so we started very simple with that, and then we switched to notes and pitches, and it was seamless, an easy transition. So it blows my mind further what we can do next with it. What's the potential? And I don't know where I found his paper from. I'm thrilled I found it. I put it in my first book, Dungeons and Qubits. I had no real expectation that this much adventure would come out of it, but I'd say that's the key thing I learned. Not only is it possible to create something that's subjective and good, but we haven't even started yet. There's so much more that I'm waiting for more to come out of Professor Miranda's mind, just so I can work with it and see what it can do, and then have him play it back and just blow my mind some more.
Would a larger quantum computer, a better quantum computer, help you, or you're perfectly fine with just a handful of qubits?
Well, a handful of qubits are okay at this point because we worked out a compression system. So when we switched to notes and pitches, it was a 9-bit binary string, but we don't need 9 qubits. We were able to compress that, I think, down to 4 qubits, 5 qubits. The advantage of better quality qubits, though, would be in the error handling. So if we have ABC, we can generate D or E. The problem is if noise makes us generate an F, we don't have a BCF in the transition matrix, and that's a problem. So there was a lot of error handling that we had to throw at it. So you've got the simulator that is pretty precise, but it's not as interesting. Then you've got real qubits singing far better than I can possibly do, and but you get those that BCF. We just can't work with that. I'd really prefer qubits that if we want 70% and 30%, they're at least pretty close with some weird quantum fluctuations, some quantum variety, but it still has to follow the rules or you get error messages. So better qubits are better. Um, but then it's exponential. So uh, uh, 5 qubits gives us 32 different combinations. So each additional qubit doubles that. So you would need a very long, complex tune to really run out of, or to need additional qubits.
And how long does the process take? So if you take a Bach cello sonata, take it through the learning phase, how long does it take to start generating music from that?
The learning phases, with the size of the pieces that we use, was instantaneous practically. Then the slow part was running on a real quantum hardware, but as soon as we were done with it, I started thinking of new ideas of how we can speed that up. So I'm really looking forward to the next round and just uh, overhauling pieces of it like that. We can speed up the quantum part, but most of the classical parts are practically instantaneous.
It's pretty quick. I mean, it depends. It depends what we do with it. For example, I am interested in real time interaction, right? So real time is not possible yet because of the connection to the cloud and blah 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 blah. But in a hypothetical world, what I want to do is to be playing with my instrument and open a window for the quantum machine to listen what I'm playing, and then play responses back to me or accompaniments and so on. So I would like to jam with with a quantum machine. So for this reason, for this purpose, the what we've got is pretty instantaneous. We would do that, you know, in a sec. It is real time. Now, the other vein of research would be to train the system with large amounts of information. Let's say take the repertoire of John Coltrane, put in the system, and see, if the system can generate melodies that are in the style of John Coltrane, for example. So these would then depend on how many files you use to train the system and so on and so forth. But I would say that what we are doing is much faster than, let's say, in the deep neural networks and things like that. It is That's the beauty of what we've got. It's so neat, it's so simple, and so smart that it's almost unbelievable when we came up with it. I think Brian was also very surprised that such a simple, elegant mode of encoding these transitions in the amplitudes of the quantum states. It's almost as natural. Is as natural as it can be.
And it sounds, listening to you guys, it sounds like this is just the start, and there's a lot more work and additional ideas that are going on. And hopefully, we'll be able to speak again in the future with the Qubit Choir or the Qubit Orchestra or the Qubit Band.
Most
To the
definitely. Yeah, most definitely. So watch this space.
how can people get in touch with both of you to learn more about your work?
The best thing to do is to go to archive and have a look at the paper we posted up there. It's called "Teaching Qubits to Sing: Mission Impossible." And our emails are there on the paper, so just email us, and we'll be happy to interact with people out there. And most importantly, I think suggestions and ideas that things that we spot in the paper that we had not thought of before, that would be very welcome.
Excellent. So, Eduardo, Brian, thank you so much for joining me today.
It's a pleasure.